Hello astronomers, welcome back, and this week we're going to be talking about the Jovian planets. These are the gas giants, the Jupiter-like planets that exist outside of the asteroid belt in our solar system. And the first one we're going to look at is the largest planet in our solar system, and that is the planet Jupiter. It's one of the reasons why we call the gas giants the Jupiter or Jovian worlds, because they are definitely, this is the king of the gas giants, at least in our solar system. And we're going to take a look at Jupiter and Saturn, and in particular want to look at these the clouds that we see on these, because there really are some stunning features of these planets. And one of the things that really strikes us when we look at the gas giants is the structure that we see in their clouds, the different colors and all sorts of things, showing that they're very dynamic places. In fact, if you look at Jupiter through a small telescope or on a very clear night through a large pair of binoculars, you'll probably see these two brown bands. And those are the cloud bands of Jupiter. And it was one of the ways that we first learned about how atmospheres work before we could look down on the Earth's atmosphere with satellites. So I want to take a look at the clouds here on the surface, on the visible surface of Jupiter. Jupiter doesn't have a rocky surface. It's basically gas all the way down. The deeper you go, the denser it gets and the hotter it gets, but there's no surface per se. But I want to look at these clouds because these clouds are caused by materials condensing in the atmosphere, just like clouds condense in our atmosphere. And the question is, why do we see these vibrant colors? To answer that question, let's go take a look at Saturn really quickly, because when we go to look at Saturn, now this is not showing the rings of Saturn, this is just showing the surface features of Saturn. You'll notice that there are still bands on the surface of Saturn, but there are no really rich colors. There's some structure you can see of the clouds, and you can see some swirls, but there's nothing like what we see on the surface of Jupiter. And the reason for that is because the clouds in Jupiter's atmosphere are closer to the top of the atmosphere so that we can see them. If they were deeper down into the atmosphere, the absorption of radiation through the clouds and through the atmosphere itself would make it so we couldn't see these things. So that tells us that there's something interesting going on as we go deeper into these planets, and we can use that to measure the properties of the atmosphere as we go down in there. For example, spectroscopically, we can learn the compositions of these different types of clouds. Some of them are water, some of them are methane, some of them are more complex molecules. And we know from laboratory experiments the pressure and temperature when those compounds condense. And so by seeing the cloud, that allows us to measure the pressure and temperature at the surface, at least the surface we can see. So let's, for example, take one of this brownish material right here. If we know what material that is, we can figure out what temperature and pressure it's going to condense at. And if we go look at Saturn, we can find a place where we get a similar shade, but it's not as distinct. And what that's telling us is that it's deeper into the atmosphere, so it's basically obscured by more atmosphere on top of it. And what that tells us is that you have to go deeper into Saturn's atmosphere to get those higher temperatures. So by looking at these clouds, we can tell something about the temperature structure of these planets. And if you even go to places like Uranus, which is more or less a featureless ball. There's some clouds right here. You have to go even deeper inside to see those clouds. And in fact, one of the reasons why we see so much blue in Uranus and Neptune is because there's a lot of methane that's scattering the light, similar to the way we get a blue sky on Earth. But you can't see the bands and you can't see any of those clouds to speak of. And that's just because, again, those things are only going to condense deeper down. These planets are further away, they're smaller, so they tend to have, you tend to have to go deeper into them to find those same pressures and temperatures. However, because I happen to be an astrobiologist, the objects I'm more interested in are the moons of Jupiter. So we're going to take a look at those. This is one of the first large moons of Jupiter. It's called Io, and it's very close to Jupiter. It orbits with about a 2-day period, and this moon, which by the way is large enough to be a planet if Jupiter wasn't there, this moon is so volcanically active that it resurfaces itself periodically. So when we go back and take images of it, it's actually changed its appearance. And you can see examples of huge volcanoes and places where molten material has blasted out onto the surface all over it. And the reason that it is so volcanically active is because it's on an elliptical orbit close to Jupiter, and it gets slightly closer and slightly further away from Jupiter as it orbits, and that flexes the moon. And that flexing, because of the gravitational tidal heating, heats up the surface, just like when you knead a loaf of bread. That dough gets hot as you knead it. Same thing here. Jupiter is basically kneading Io, and it's getting that heat is getting distributed and causing all of this volcanism. If you go further out from Jupiter, that same process is happening. That tidal heating is happening, but it gets less and less and less. So if we go to the next large moon out in Jupiter, this is a moon called Europa, and Europa also has been resurfaced because of this tidal heating, but not to the extent that Io has. And you can see it's been cracked and flexed and all this stuff, but it's not nearly warm enough to cause the same type of volcanic heating that you see on Io. And in fact, it is warm enough, however, to have liquid water underneath this icy crust. So we know this is ice because we've looked at it with spectroscopy. We know it's made out of water. These cracks tell us that this water is being flexed. And if you zoom in, you can even see regions where the material has been broken up into pieces and even punched through by impact craters, and about anywhere from 10 to 100 kilometers beneath the surface is a vast liquid water ocean. And that gets us astrobiologists excited, because wherever you have liquid water, on Earth anyway, you have life. And there's no reason, considering all the materials necessary for life are in this object in terms of the elements and the compounds needed. You just need an environment where there's energy and some sort of fluid to move things around, and we've got liquid water, and there's probably some volcanism which gives it some energy that's not too different from the subsurface ocean, the ocean depths of our own planet. And so who knows, maybe there's something living in this ocean that's underneath the surface of icy Europa. And as we go further and further out, we see, this is the moon Ganymede. Now you'll notice we see more craters, and those more craters means it's less active surface. It's further from Jupiter, so we're getting less tidal heating. And then if we go out to Callisto, same thing. We see, again, more craters, less of the other processes that are causing this type of tidal heating erosion. So the moons of Jupiter are pretty interesting because they are worlds in their own right, some pretty fascinating places. Now, the last thing I want to show you about the outer solar system was the most surprising thing we found in the last 50 years, as far as I'm concerned. We'd sent a probe to Pluto, and Pluto up until this point had been at best a fuzzy blob taken by the best telescopes on the planet. We had never been close enough to see the surface of Pluto. And because it's so far away from the sun and it's not orbiting a giant planet, we expected it to be a very cratered, dead-looking world with very little surface features. It might look like Callisto. It might even look like Mercury. You know, not something terribly interesting, but certainly some old dead rock that's been floating around out there. So NASA, being who NASA are, they decided to send a probe out anyway. And if we imagine what it looked like, as we approached it, we started to see more surface structure than we'd ever seen before. Still, though, looked a little bit more like Callisto. And then as we got very, very close, the New Horizons probe took these images, and they're I'm going to go around to the high resolution. It did a flyby, so some of the images are very high resolution and some of them not so much because they're moving away. And we see this incredibly active surface. In fact, there don't appear to be a whole lot of craters. There are a few, but there's an enormous amount of geological activity that we weren't expecting. And in fact, scientists now are still trying to work out what's going on the surface of this world. You can see that there's crags and bumps and wiggles that are not obviously associated with craters. There are these smooth patches, which again, if you see a smooth patch without craters, it must have been resurfaced recently, so we're not sure exactly why that's happening. It's really an amazing place, and it just goes to show you that you never know what you're going to find. Our expectations are often wrong. There's clearly geological processes happening out here that we don't fully understand. Now, one of the things, the advantage that Pluto has is it has been out there for about 4.5 billion years, and these processes have been acting for a very, very long time. So whatever's happening, people suggest that this could be caused by a very thin atmosphere that periodically pops up because Pluto occasionally gets closer to the sun because it's on an elliptical orbit. There's people studying these things as we speak, but it's just goes to show you that you never know what you're going to find. All right, that's a little review of some of the aspects of the outer solar system. You're going to be exploring more of that, including Saturn's moon Titan. I've got a nice video of that to show what that looked like when we descended down onto the surface. After this, we're going to finish up on the solar system and move out to looking at how we measure the distances to stars and determine all of their properties. So we'll see you then.